Hello everyone and welcome back to another video. Today we're going to talk about reciprocal functions. Now before we get into it, let's go ahead and review what reciprocals are. If we were to think about the reciprocal of a number, we're really just thinking about the inverse of some sort of given number. For example, if we look at the number 4, the inverse of 4 is going to be 1 over 4. Now where that 1 comes from is in our original number, the 4, we can think of this as 4 over 1. So really all we're doing is we are switching your numerator and your denominator to give us the reciprocal. Another definition for reciprocal is we have a second number, for example, the reciprocal of, let's say, -3 would be -1 over 3. Because if we were to multiply these two numbers together, -3 times -1/3, our result is going to give us a +1. So another definition of a reciprocal is a second number or expression that when we multiply it by the original gives us a product of 1. So that being said, we can take a look at a couple of quick examples here. If we think about the reciprocal of a fraction, for example, let's go with 2/3. The reciprocal is going to be 3 over 2. And if we look at a negative fraction such as -4 over 7, your reciprocal is simply going to be -7 over 4. Now, some of you guys might be a little bit confused about where that negative goes, if it goes to the top or the bottom number. Really, for this example here, if I put the negative in front and I put the 4 over 7 like that, this is really the same thing as just putting the negative onto the 4 or the negative onto the 7, like so. Again, depending on the application or the situation that you're using, you can adjust where that negative is. For us, when it comes to reciprocals, we just want to essentially keep it on the top or on the side typically. What we're going to do next is look at a few examples of how to plot reciprocals if we're given certain points. For example, let's say we have a value of, or an ordered pair of 1, +2. So that would mean that our point is going to be right there. So everything in our blue is going to be our original function. So let's say original f of x. And then everything in red is going to be our reciprocal function. So if we're looking at our point here, we have 1, 2. Our reciprocal is going to only be looking at our y values. So if our y value here is 2, the reciprocal of 2 is going to be 1/2. So that would mean that this point here, the reciprocal of this point, is going to be at 1, 1/2. So 1, 1/2 is going to be roughly there. If you look at another example, let's say if we're looking at, let's say -2, +4. So -2, +4, the reciprocal of this, because we're looking at the 4 there, the reciprocal of that would be 1/4. So that would mean our reciprocal point would be right down here. So the reciprocal of 4 we said was 1/4, which is right about there. Now that we've taken the reciprocals of some whole numbers, we can look at some reciprocals of fractions. Let's say, for example, we have this point right here. So we're looking at -4. And let's say that this is, +1/2. So the reciprocal of 1/2 is actually 2, or 2 over 1. So my reciprocal of this point here is going to be right here. And we're still at -4 for our x value, but our y value is now at +2. Looking at some examples where we have some negative values, let's go ahead and plot one down here. Let's say we're at 3, -2. So 3, -2. The reciprocal of -2 is now going to be -1/2. So our reciprocal, we're still at +3, but we're looking at -1/2 right there. So this would be 3, -1/2. And if we were to put one right on the y-axis here, let's say, for example, if we're looking at this point, let's do that in blue. If we're looking at this point right there, we know that's going to be 0, -4. The reciprocal of -4 is going to be -1/4. So this 0, -4 is now turned into 0, -1/4. So 0, -1/4 or -0.25. So let's come up with a few observations from what we just did. First of all, the reciprocal of a positive number, reciprocal, if I could spell, reciprocal of a positive number is positive, and the reciprocal of a negative number is still going to be negative. So those are two observations that we've made so far. Now, the next thing we're going to ask ourselves is surrounding some particular numbers that we didn't look at earlier. Let's say, for example, we were looking at the point 1, 1. Well, this is going to be a really special point along with a point such as -1, -1. And the reason why these points are going to be very interesting, if you haven't already thought about it, is if we consider the reciprocal of 1 and -1, the value remains unchanged. So, like I said, the reciprocal of 1 is still 1 because 1 over 1 is the same thing, or the reciprocal is just 1 over 1. The reciprocal of -1, we can think of that as -1 over 1. Well, we have 1 over -1 or -1 over 1. So realistically, so essentially, the reciprocal of 1, -1 remain unchanged. And we have a special name for these 2 points. So these 2 points, we actually call these invariant points. And they occur whenever your y value is at 1 or -1. So let's go ahead and write that down as a third observation. So we have invariant points, and invariant points occur when y is equal to +1 or when y is equal to -1. So these points do not change from the original to the reciprocal. So if we were thinking of anything along y is equal to -1, so this point right here would also be an example of invariant point. This would be an invariant point in the reciprocal. This would also be an invariant point in its reciprocal function. Okay, so we've come up with one of those special points that we want to talk about. Now, the last thing that we want to bring up before we actually start to graph some functions is what happens if our y value is 0. So let's go ahead, let's clear this off a little bit. And then we're going to consider, well, what happens if we try to take the reciprocal of the value 0? So let's look at this point right here. So we're looking at -2, 0. Well, the reciprocal of 0, you can think of that as 1 over 0. Well, up until this point, we know that we cannot divide by 0. So right now, when we're trying to divide by 0, we can say that this is undefined. So once we find out that something is undefined, it actually creates an invisible line. And this invisible line, let's go ahead and draw this invisible line right here. See if I can stay on the line right there. So this invisible line at x is equal to -2 is what we call a vertical asymptote. So this is what we call a vertical asymptote. And this vertical asymptote appears whenever we're taking the reciprocal of the value 0. So if we had a point on the original function that was here, in the reciprocal function, we would also have another vertical asymptote right there. So essentially, when we're looking at any points that are on the x-axis, aka your x-intercepts, we are looking at a missing piece of your graph, which create our vertical asymptotes. So again, if I were to have a x-intercept right here at +3, we can't take the reciprocal of 0, so we would end up with another vertical asymptote right in this, or right on that line there. So there are no values that exist at x is equal to 3. So that gives us our fourth observation here, is that your x-intercepts of the original function are equal to your vertical asymptotes of the reciprocal function. And again, this idea might not be so clear now, but when we look at some examples of actual functions, things will start to click. So now that we have a better understanding of what reciprocals are going to look like on a graph, let's go ahead and graph some actual functions. So if we were to think about the original function of y is equal to x plus 1, well, the reciprocal of this is really just going to be y is equal to 1 over x plus 1. So all we're going to do is take our original function and put it underneath as our denominator, and the 1 is going to stay on top. Similarly, if I were to take the example of y is equal to x squared, the reciprocal of this would be y is equal to 1 over x squared. We'll take a look at quadratic functions in just a little bit, but we'll start with our linear function right here, y is equal to x plus 1, and then we're going to graph its reciprocal function as well. So if you recall from Math 10, there are a couple of characteristics we can see about this graph already. First of all, our slope is going to equal to 1, because we can think of that as 1x. And then your y-intercept also happens to be 1 as well. So we're going to start off by plotting our point here at positive 1. So we have 0, positive 1 as our y-intercept. And since we have a slope of 1, we're just going to go 1 up, 1 to the right, and we're just going to keep doing that until we reach the end. We can go the opposite direction where we go 1 down, 1 to the left, and we're just going to do that again until we reach the end there. And then we're going to connect our line or our points here with a straight line, and then I will color this blue. Let's go ahead and do that. And we've got a nice straight line there where I have y is equal to x plus 1. Now, in order to graph its reciprocal, what we're going to need to do first is identify the x-intercept. So in order to find the x-intercept of this function, we're going to look at the graph as well as solving it algebraically. So if we were to look at the graph here, we can see that your x-intercept, or rather where your graph crosses the x-axis, is when x is equal to -1. If we were to do this algebraically, we would just simply set y is equal to 0. Let's do this instead. 0 is equal to x plus 1, and we have -1 is equal to x. So your x-intercept is at -1. So on our previous page, what we found out was that the x-intercept of your original function is going to be the vertical asymptote of your reciprocal function. So that means that we have a vertical asymptote at x is equal to -1. So what I'm going to do is I'm going to draw a vertical line, and I'll do it as a dashed line here, where I have my vertical asymptote right there. The next thing we're going to do is identify where your invariant points are. So your invariant points, or points that don't change from the original to the reciprocal function, there's going to be one right here at the yellow when y is equal to -1, and one right here when y is equal to, oops, that's not positive 1, one right here when y is equal to positive 1, or where it happens that our y-intercept is. And the reason why we want to identify those graphs or those points on our graph is that they'll help us figure out exactly where our graph is going to end up or what our graph is going to look like. So let's look at a few points on our original graph that we're going to take the reciprocal of. So first off, let's do something such as this point right here. So let's start off with our -2's and +2's. So you can see here that when y is equal to -2, our reciprocal is going to be -1/2. Same thing over here on this side. When your y value is +2, your reciprocal is +1/2. Let's look at some bigger examples. Or different examples. When y is equal to -1/3, your reciprocal is, let's look at some different examples here. Let's look at some different y values here. So when your y value is equal to -3, the reciprocal is -1/3. And maybe let's look at one more here. When y is equal to -5, your reciprocal of -5 is -1/5. So we can see here that we start to creep closer and closer, and maybe if we're going this direction, we start to creep closer and closer and closer to our x-axis here. And if we were to extend this and we say, like, let's go down here, Well, what's the reciprocal of negative 100? Well, the reciprocal of negative 100 is negative 1 over 100, which is really, really quite small. So you can see that this red line would get closer and closer to our x-axis. And even if we were to go up until negative 1 million, the reciprocal of negative 1 million isn't quite exactly equal to 0. It gets very, 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 very close, but it doesn't quite equal to 0. As we start to creep closer towards our invariant point of negative 1, so we start to creep closer there, we can look at some other examples. So let's say we were to look at this point right here when y is equal to negative 1/2. Well, the reciprocal of negative 1/2 is going to be positive 2, so we can put a point right here. We can think of another example where we could have potentially, let's say, negative 0.1. Well, the reciprocal of negative 0.1 or negative 1 over 10 is simply going to be negative 10. So we can see that these points start to creep closer and closer and closer to the vertical asymptote over here. So now we're going to switch gears a little bit. Let's go over to the other side and let's think about what happens with these values. If we're looking at this value of 3 when y is equal to 3, the reciprocal of 3 is going to be 1/3. The reciprocal of 4 is 1/4, and the reciprocal of 5 is 1/5. So maybe I don't want to put it right on there. But you can see that as we start from our reciprocal of 1 or our invariant point of 1, we start to actually creep closer and closer and closer to our x-axis again. We don't quite cross it, but we get very, very close. And once again, if we were to go the opposite direction, let's think of if y is equal to 1/2. Well, the reciprocal of 1/2 is going to be 2. The reciprocal of, let's say, 1/10 is going to be positive 10. So this point here, right here, if we were to look at it, and if we were to imagine, well, the reciprocal of that point would be a point up over here. So we can see that this is going to start to creep very, very, very close to that vertical asymptote there. And I realized I should probably draw this in a different color. Let's do this in green. So we can see that those values get very close to that vertical asymptote, but they do not ever cross. And a second observation that you might have seen is that they also get very, very close to our x-axis, or otherwise this invisible line of y is equal to 0. And we actually call that a horizontal asymptote here because we do not cross we do not cross that line of y is equal to 0. So we have a vertical asymptote here. So in summary, all we're going to do when we are graphing the reciprocal of some sort of graph is we're going to first look for the x-intercept of the original. We're going to find the vertical asymptote of the reciprocal function. And then we're going to look for the invariant points when y is equal to 1 or negative 1. And then using points from our original graph, this blue line, we're going to start to graph our reciprocal function. Now, one last thing that I want to bring your attention to is if we look at your reciprocal function here, and if you've already taken a look at rational expressions, we'll notice that this expression of 1 over x plus 1 has an NPV, or non-permissible value, where x cannot equal to negative 1. So your NPV here is also related to the rest of our graph here. And let's go ahead and make another observation. We can now state that the x-intercept of the original graph is equal to the vertical asymptote of the reciprocal, which is really just equal to the NPVs of the reciprocal function. All right, let's take a look at a few more examples. So for this first question, we're going to state the equations of the vertical asymptotes of each of the following functions. So what we're going to do is we're going to take a look at the original function. So our original function here is 3x plus 2. So we can think of this as y is equal to 3x plus 2. And remember that our relationship was that the x-intercepts of the original are equal to the vertical asymptotes of the reciprocal functions. So what I'm going to do is find our x-intercepts of the original by setting y is equal to 0, and then we're going to solve for x. So let's subtract 2 from both sides and then divide both sides by 3. So that means that my vertical asymptote of my reciprocal is x is equal to negative 2/3. For my second example, we see here that we can actually factor out an x. So the original function would have been y is equal to x cubed minus x squared minus 12x. And I'm just going to factor out an x, and I'm left with x squared minus x minus 12. And we can actually factor it one more time, where I have x minus 4 and x plus 3. So looking at our y value here, we're going to substitute that with a 0, and we get 0 is equal to x times x minus 4, x plus 3. And from here, we know that we have 3 x-intercepts. X is equal to 0, positive 4, and negative 3. So that means that our vertical asymptotes will occur at x is equal to negative 3, 0, and positive 4. So looking at this next example, we have our original function of y is equal to 2x minus 3. And we need to graph both the original and the reciprocal without using our calculators. So starting us off, let's go ahead and find out the equation of our reciprocal function first. So that means all we're going to do is we're going to take a1 and put this 2x minus 3 underneath. So our reciprocal function is y is equal to, let's make that neater, y is equal to 1 over 2x minus 3. If we're looking at our vertical asymptotes here, remember all we're going to do is take our original function and figure out the x-intercept. So here we're going to take y is equal to 2x minus 3, set our y value equal to 0, and we're going to solve for x. So let's add 3 to both sides and then divide both sides by 2. So in our original function here, we have our x-intercept of 3 over 2, which is 1.5. So our x-intercept is going to be right there. And again, from Math 10C, we can find a second characteristic. Our y-intercept is actually going to be at negative 3. So I'm going to go ahead and plot that down as well. So we can figure out that that line is going to start to pass through those 2 points. Again, our slope is going to be a positive 2 due to this coefficient of 2 on the x. Remember, we have y is equal to mx plus b. If you need a quick review, you can take a look at my slope videos as well. So that means starting from here, we're going to move up to 1 to the right, up to 1 to the right, up to 1 to the right, and we can graph our original function. Let's go ahead and draw a straight line through those points. Let's go ahead and do that. Let's adjust this a little bit. And we have our graph of y is equal to 2x minus 3. Let's go ahead and label it. Y is equal to 2x minus 3. And what I'll actually do is I will do the reciprocal in blue. So let's rewrite this. Y is equal to 1 over 2x minus 3. So since we know that our x-intercept is 3 over 2, then that means that your vertical asymptote occurs at x is equal to 3 over 2. So let's go ahead and draw a vertical line. Let's go do this with straight line like so. And let's make it a dotted line. So we got that. So now that we've drawn our vertical asymptote, we're going to identify some points that we can use to help us graph the reciprocal. So first off, we're going to look at your invariant points here. So our invariant points, and maybe I'll do this in an orange. So your invariant points are when y is equal to 1 or negative 1. So you can see here on the graph that we have an invariant point at 2, positive 1, and another invariant point here at 1, negative 1. So basically when y is equal to 1 or when y is equal to negative 1. So that's where our invariant points are going to be. Gone ahead and highlight them in orange here. We can also look at something such as the y-intercept, and we know that the y-intercept is going to be over here. So the reciprocal of the original y-intercept is going to be negative 1/3. So remember, the original y-intercept is negative 3, so the reciprocal is going to be negative 1/3, which is going to be roughly about here, let's say. We know that there's going to be another horizontal asymptote at y is equal to 0. So we can go ahead and I'm just going to copy and paste another dotted red line. Let's go ahead and turn it sideways so it's horizontal. And we're going to put that all along the x-axis here. So again, these two dotted lines are going to be reminders that we cannot cross those red lines while we are graphing our reciprocal functions. So looking at some examples or some different points that we could have here, if we were looking at y is equal to negative 1/2 on the original, so our original was right here, the reciprocal of negative 1/2 is at -2. So this point goes from here to here at -2, and I could continue to draw more points coming down and following along our vertical asymptote there. I can do the same on the opposite side. We can look at when y is equal to +1, the reciprocal, or positive 1/2. The reciprocal of positive 1/2 is +2. We can look at some other examples, such as the reciprocal of 5. The reciprocal of 5 is 0.2, or 1/5. The reciprocal of 4 is 1/4, or 0.25. The reciprocal of 3 is 1/3. So we're going to put another point there. And we can see that we can start to draw our line or a curve and follow along that horizontal and then the vertical asymptote as well. Same thing on the other side. If we look at something such as our reciprocal of -5, our reciprocal is going to be -1/5. So we can see that this line starts to creep up this way and follow along our horizontal asymptote. And there you go. We have our reciprocal function here of y is equal to 1/2x minus 3 being graphed out alongside the original function of y is equal to 2x minus 3. So now we're going to take a look at some quadratic reciprocal functions. And we have here y is equal to 1/x² minus 2x minus 3. All we're going to do is look at the original function first and figure out what the vertex is by looking for the x coordinate and then using that to find the y coordinate. So let's go ahead and state the original function. So the original function is simply going to be y equals x² minus 2x, minus 3. There's another way that we could do this too, because this is factorable. I'm just going to go ahead and write this as x minus 3, x plus 1, x plus 3, or x minus 3, x plus 1. And we can actually just plot that here. We have an x-intercept. We have x-intercepts at x equals 3 and -1. So we've gone ahead and done that. So due to symmetry, we can see that we should have our vertex at +1. Remember that x-intercepts are going to have a symmetrical line going straight down the middle. So 2 units away from 3 is 1, and 2 units away from -1 is also 1. So our axis of symmetry is going to go straight through x is equal to 1. So what we're going to do is plug that 1 into our original here. So y equals 1² minus 2 times 1 minus 3. And that gives me 1 minus 2 minus 3. And we have a y value of -4. So for us, our vertex of our original graph is at 1. And I'll write that here, vertex at 1, -4. So 1, -4 is going to be right down here. We can tell that our y-intercept is going to be at -3. So again, due to symmetry, if our axis of symmetry is right here at +1, and we're looking 1 unit over to the left for my y-intercept for a point, there's going to be another point right here as well. Let's go ahead, quickly sketch through those points, or draw a quick sketch of our points through there. We get roughly something that would look like this. So now what we're going to do is we're going to turn our attention over to the reciprocal function. We're going to look for the vertical asymptotes. Now remember what we said earlier, that our x-intercepts of the original were the vertical asymptotes of the reciprocal. So that would mean that based off of what we wrote down here, our vertical asymptotes are going to be at x equals -1 and x equals 3. So let's go ahead and draw two vertical lines here. And we're also going to draw one here. We're going to make them both green, let's say. Let's do that. Let's make them both green. So I've got one green line there. And let's make it a dotted line. Let's do a second green line, and let's make this one a dotted line as well. So we have our vertical asymptotes in place. And now what we're going to do from here is we're going to look at, let's say, the y-intercept. So what we're going to do next, once we have those vertical asymptotes in place, let's go ahead and write that down here. Vertical asymptotes at x equals -1 and x is equal to +3. The y-intercept of the original and the reciprocal, well, we know that our original was -3, so the reciprocal is y is equal to -1/3. So -1/3 is going to be, let's say, somewhere over there. If we're looking at the horizontal asymptote, it's just y is equal to 0. And if we're looking at our invariant points, we're going to have one that is going to be situated right here when y is equal to -1. We're going to get a second invariant point right here. We're going to get a third one here at y is equal to +1. And we'll also get a fourth one right about there. Well, some of you guys might be wondering, how do I find the invariant points algebraically? All we're going to do is take a look at our original function, y is equal to x squared minus 2x minus 3, and we're going to replace the y with either +1 or -1. So let's go ahead and take a look at how we would do that. 1 is equal to x squared minus 2x minus 3. Let's move that 1 over to the other side. So I get minus 2x minus 4. So we'll notice that we can't factor this normally. So we would have to use the quadratic formula where a is equal to 1, b is equal to -2, and c is equal to -4. So all in all, when I go ahead and use the quadratic formula to find my corresponding x values, I would get +2 plus or minus the square root of 8 divided by 2. And I can actually simplify this to 2 plus or minus 2 square root 2 over 2. And further simplifying this would give me 1 plus or minus square root 2. So that's what happens when I plug in a 1 for a value of y. And we're going to have to do the same thing where I would plug in a -1 is equal to x squared minus 2x minus 3. And I would find essentially 2 more x values that would give me the corresponding x values of my other of these two invariant points here and here. Now, when it comes to actually graphing the reciprocal function itself, I like to start off with the vertex. So the vertex here, we had a y value of -1/4, or -4 rather. The reciprocal of -4 is -1/4. So let's go ahead and plot that up here. We already know that our reciprocal of the original y-intercept was -1/3. So that means that I also have a -1/3 on this side. And as we start to draw our graph starting from our invariant points, we can see that we've got a nice smooth graph that comes up pretty close to the our x-axis there. And as we start to come across this way, we're going to start to once again look at this as an example. If we have -1/2 here, the reciprocal of -1/2 is -2. So that would mean that we start to come down this way along our vertical asymptote. And I would do the exact same thing on this side as well. Now, when it comes to these two invariant points, I didn't draw these so great originally, so let's go ahead and do this. Let's make this look something like this. I'm gonna make this a little bit more clear to understand here. So let's do something kind of like this. So that's what more or less what our graph should look like. Get a little bit more space there, just so I can show you guys what I'm talking about here. Yeah, let's go ahead and do that. So again, to highlight our invariant points, we had 1, 2, 3, and 4. So looking at our examples here, let's say, for example, if this was a +4, the reciprocal of +4 is +1/4. The reciprocal of 2 is 1/2. So you can see here that our graph would kind of curve up this way towards this invariant point, and we would do the same thing along this side here. And really these would follow along our x-axis. And if we were to go the opposite way, the reciprocal of 1/2 is positive 2. So we can see that our line starts to curve up this way on this side, and it starts to curve up along here on this side. And maybe I won't draw it right on our vertical asymptote. I'm trying to. There we go, a little bit better. So that's going to go all the way up essentially. And we can see that we have our reciprocal function. So again, just to summarize how we did this question, we graphed our original quadratic. We found some points such as the y-intercept and the vertex. We find our x-intercepts, which are actually our vertical asymptotes of the reciprocal function. We look for our invariant points, and we start to draw our reciprocal using our known points. And then we start to use a little bit of logic to figure out which way along the vertical asymptotes our reciprocal lines will follow. So now what we're going to do here is we're going to look at some examples of reciprocal functions that are given to us, and we have to try to find the original functions. So the way that we're going to do this is by starting off with our vertical asymptotes and figuring out what the x-intercept was that gave us that vertical asymptote. So we can see here that we would have a vertical asymptote at x is equal to -1. So x is equal to -1 is our vertical asymptote, which means that it's going to be your x-intercept of the original. So you have an x-intercept at x is equal to -1. We're going to look at a second point that's given to us. So we're given a point of -2, -1/4. So -2, -1/4 means it's right here. So the reciprocal of -1/4 is going to be at -4. So let's go ahead and plot our 2 points, so our x-intercept. And we also have that point there at -2, -4. And we can actually start by drawing a line through those 2 points already. So let's go ahead and do that. I'm going to do that in green. So our line should look something like this. And what we're going to do is use a little bit of math to help us figure out what the slope between those 2 points should be. If we were just to use the graph itself, we would see that it goes up 4 and then 1 to the right, meaning that our slope should be 4, but we're going to use the slope formula to help us figure that one out. So let's go ahead and do that. So once again, our x-intercept of the original should be at -1, 0. Let's go ahead and use our slope formula. We know that m is equal to y2 minus y1 over x2 minus x1. So this means that we would have 0 minus -4 divided by -1 minus -2. This gives me a +4 over +1, which is just 4. So now that we see that our slope is 4, I can tell that my original graph here was a little bit crooked. I didn't see exactly where the x-intercept was due to that giant x-intercept there. I'm going to shift this very, very slightly so we get a little bit more of an accurate graph. We can see that our y-intercept rather should be at 4, but we're going to verify this algebraically just so we know that we're not going crazy. So let's go ahead and just write that down. M is equal to 4. So our slope is 4. And we're going to use the formula y is equal to mx plus b to help us algebraically confirm that our y-intercept or b value should be 4. So using our x-intercept from earlier, -1, 0, that gives me my x and y value here. So I'm going to substitute 0 is equal to 4 times -1 plus b. So we get 0 is equal to -4 plus b. And we can confirm that our b value should be equal to 4. Meaning that our original function should be y is equal to 4x plus 4. At this point, feel free to pause the video, try out this next question on your own, and then unpause once you're done to check your work. Now let's take a look at a graph of a reciprocal function of a quadratic to figure out what the original quadratic should look like. So first of all, looking at our vertex here, we know that our vertex is at a value of 1/2. So the original vertex would be the reciprocal, or would have a y value of the reciprocal of 1/2, which would mean that the vertex is right here at 1, 2. Another point that we can use to help us plot the original quadratic is going to be our invariant point right here at +1. So we have 1 there, and we also have 1 there. We know that our vertical asymptote is going to occur somewhere around there. We don't know exactly what that vertical asymptote is yet. We're going to have to figure out what the original is, and then we could figure that out later if necessary. But that means for us, because that is our vertical asymptote, that means that the original x-intercept should land right there and right there roughly. We can look at another 2 points. First of all, when y is equal to -1, we have another invariant point here and another invariant point right there. So if I were to sketch my original, it would look something like this. So roughly I get something just like that. Oh, that right-hand side was awful. Ugh. This is much tougher than it looks, guys. Let's go ahead and do that. Okay. So for us, let's go ahead and figure out what the actual equation is. So we've got 2 points that we can use. We know that we have one here at 1, 2, and we've got another point here at 0, 1. So that means that P is equal to 1, Q is equal to 2. We're going to use this XY coordinate, meaning that X is equal to 0, Y is equal to 1. And we're going to plug this into our vertex equation here, or vertex form equation. So y is equal to a times x minus p squared plus q. So we have 1 is equal to a times 0 minus 1 squared plus q, which was 2. So we have 1 is equal to a times 1, which is just a, plus 2. So in this case, we get a is equal to -1. So again, that checks out because we know that our quadratic should open downwards, meaning that our a value should be negative, meaning that our final equation for the original quadratic should be y is equal to -1 times x minus 1 squared plus 2. This one here can be a little bit tricky because, first of all, most of you are probably thrown off by the fact that we only have one vertical asymptote there. So let's go ahead and sketch our vertical asymptote. So we have a vertical asymptote of x is equal to +3, meaning that the x-intercept of the original is going to also be at x is equal to +3. Once we use our invariant points to help us figure out 2 other points, we'll have 1 here and we'll have 1 here. Things will start to make a bit more sense because now you can see that we're going to have a quadratic that only has one x-intercept. It just barely touches that x-axis, so we only have one x-intercept. So continue on with the rest of my parabola. We should get something that looks kind of like this. Again, I'm not going to worry too much about where that y-intercept is for this example. We're just sketching it. But we've got 3 points here. And what we're going to do is we're going to use our vertex. So we know our vertex was at 3, 0, and a secondary point of 2, 1 to help us figure out what our original quadratic was going to be. So from here, all we're going to do is identify our P and Q. So P was 3, our Q was 0, our vertex. And we're going to use a second point on that same parabola. So 2, 1. So that means that x is equal to 2, and we'll have y is equal to 1. We're going to plug this into our vertex form of y is equal to a times x minus p squared plus q. So we'll have 1 is equal to a times 2 minus 3 squared plus 0. So I'll have -1 squared, which is just 1. So 1 times a is a, and I'll have a plus 0. So I get a is equal to 1. So that means that my original function was simply y is equal to 1 times x minus 3 squared, and that's it. So for this last one, it looks quite peculiar. We can see that we have no vertical asymptotes, but we do have a horizontal asymptote here. So we're going to start off by looking for the reciprocal of the 2 points that are given to us. So the reciprocal of 1/2 is a +2. The reciprocal of 1/4 is +4. And again, due to symmetry, our axis of symmetry would be right here at -3. So if I'm at +4 here, I'm also at +4 right here. So our graph, or rough sketch, should look something like that. And once again, let's go ahead and write our coordinates. So -3, +2. And we know that this one here is going to be at -2, +4. From here, we're going to use those 2 points to help us figure out the original equation. So y is equal to a times x minus p squared plus q. We know that p is equal to -3, q is equal to 2, x is equal to -2, and y is equal to 4. So plugging in all of those values, we will get 4 is equal to a times -2 minus a -3 squared plus 2. And we'll end up with 4 is equal to positive a, because we'll have -2 plus 3, which is just 1. 1 squared is 1. So 1 times a is a. And we'll have a plus 2, and we will get a is equal to 2. So plugging this back into our equation, we will have 2 times x minus a -3 squared plus 2, or fully simplified, we'll have x plus 3 squared plus 2. One last thing that I want to touch on that we didn't mention earlier on in the video is talking about the domain and range of reciprocal functions. So how would we write this out? And whoops, one thing I realized, we're missing a horizontal asymptote for this graph here. Let's go ahead and resketch that. So for our domain, we know that we have two vertical asymptotes, one at x is equal to -1 and x is equal to +3. So for us, our domain, we would simply say that we have the set of all x values such that x cannot equal to -1 and +3. Other than that, x is an element of the real number system. So essentially all we're saying is that as long as x does not equal to -1 or x cannot equal to 3, everything else is fair game. If we were looking at the range, on the other hand, we already know that we're looking at the set of all y values such that we already know that we have a horizontal asymptote at y is equal to 0. So you just say y cannot equal to 0. And then we could also include the conditions that y has to be greater than 0. And if we're looking at our vertex here, like I had to remind you guys, we're at 1, and this is going to be -1/4. And y also has to be less than or equal to -1/4. And y is an element of the real number system. That brings us to the end of today's video. I apologize if it felt a little bit rushed near the end because I am in a bit of a time crunch. If you have any questions, feel free to leave them in the comments below. Thanks again for watching, and I'll see you in the next video.